All right. Thanks for that intro there, Isaias. It's always good to have someone take over our dreams, I guess. Never comes to math class again, runs and hides in a corner. All right, so let's start talking about those matrices. Um, how did the 7.03 assignment go? Any major questions? Anything you want me to review again as far as the calculator goes? Good, you're good? There was a typo. So I just want to point out there was a typo on one of the questions. I think Rachel caught it first. Some of you may have also caught it, but then just corrected it on your own. The question where it was talking about the Gaussian elimination, and it gave you that system of equations, and there were three equations with three variables. The very first equation in that example had two x terms in it, and the last x term was actually supposed to be a z instead of an x, so that was a typo. In my defense, x and z are right next to each other on the keyboard, so I'm going to just stick with that. But there was a typo there. It was supposed to be an XYZ variable in each one. So if you didn't get that one correct, and you're going to do corrections on it because you accidentally combine the X's instead of realizing there was a typo there, I will give you full credit back for the correction that you do with it. So it won't be just half credit back, it will be full credit back. I want to say it was like question 3 or something like that, or question 4 on the 7.03 assignment. It was the one on the Gaussian elimination, I know that. If you haven't gotten to that assignment yet, it has been fixed, so you have nothing to worry about. You won't even notice there's a mistake. So I apologize for that typo being in there the first time around. Any other questions with that 7.03? All right, then I want to say there's only 4 lessons to set to Unit 7. Does that sound right? Anybody more? Yep, I think there's only 4 lessons to this unit. Okay, I thought so. I'm working a little bit ahead of you guys though as far as prepping goes, so I couldn't remember exactly how many lessons there were, but we're entering the last lesson already of the unit. Woohoo! So a very short unit. In fact, some of the upcoming units are going to be pretty short. Unit 8's a little bit lengthier, but the rest of them, they're pretty short. There's not many lessons in each unit, but there's a lot of content that's in the lesson, so it does take a while. So as we start progressing, especially when we hit Unit 9, you'll notice that it's not uncommon to have like 3 or 4 days per lesson, because there's a lot of information that we've got to cover in that one lesson. So it can easily be stretched out for that amount of time. So heads up with that. Some of the lessons coming up are going to be like 3 to 4 days when we hit that Unit 9. All right, so the last lesson of Unit 7 here, we are talking about systems of inequalities in 2 variables. So this hopefully will be a nice review for us. We're back to just the 2 variables, x and y, which means that we can graph using GeoGebra or your Desmos. If you prefer to use Desmos, that's fine. And we're also going to talk about not only systems of inequalities, but we're going to be looking at our linear programming a little bit as well. So we're going to put those systems of inequalities to use in our practical everyday life, and we're going to look at how linear programming comes into play with that. What's really nice though is that the first couple slides here are going to be simply strictly review all the way back to kind of your Algebra 1 days, believe it or not. So the first thing we have to refresh ourselves on is just graphing an inequality. And this will go really, really fast because like I said, this is a very, very basic algebra concept, right? But sometimes it's those basic things that we forget. So we're going to get a quick refresher here. we have the inequality y is greater than or equal to 2x plus 3. We not only do we want to graph it, but we're going to state the boundary of the region as well. All right, so let's talk about the graphing. How exactly would I graph this inequality? Can anybody remember or kind of walk me through the steps that they would do to graph that? The first thing you got to recognize is maybe a dashed or solid line is going to come into play. Yep. And then shading above. And Tommy says solid line and shade above the line based off the inequality that's there. Exactly. Now we have to actually figure out where the line is going to be, right? That's another big part of it. So Isaiah says to find out where the line's going to be, we're going to actually start with the y-intercept. Yep, so what is the y-intercept of this graph? A 3. And then what do I do after I find the y-intercept? You're going to find the slope and use that to help you find additional points. Follow the slope of 2 over 1. Yep, so remember that value in front of the x, if it's in slope-intercept form, is your slope there. I'm just connecting here. You can also go down 2 to the left 1, right? That's the same thing as a positive 1, down 2 to the left 1, a negative over a negative. All right, I think Tommy said that we are going, and Isaiah said as well, we're going to connect this with a solid line. How did you guys know it was going to be a solid line versus a dashed line? The equal bar underneath, thank you. Yep, the equal sign underneath the inequality means it's included. Yep, and then the shading, Tommy said, was going to be above the line or in y-intercepts greater than what we graphed. So how do we know that the shading was going to be above the line? Y is greater than. Yeah, if we look at the inequality symbol, that's a greater than. So we want numbers bigger than the y-intercept there. Good. What does the shaded region represent? Your solutions. Yep. If I were to pick a point on the line, would it be included in a solution? As a solution, I should say. Why? Good. So does that mean that every inequality we graph, no matter what the symbol is, I can pick a point on the line and it will be included in my solution set? Good. Only points on the line that have a solid line connecting them can be included in your solution set, right? If it's dashed, you cannot include those points in your solution set. Really good review. Good. All right, now they do have a couple of terms highlighted below here. And they just talk about the half plane. The half plane is simply the kind of the shaded piece of it all there. It also talks about the boundary of a region. So what do you think is going to be the boundary? When you hear that term boundary, what do you think that refers to? The line itself, yeah, so the line itself is going to be our boundary line. Now, when we talk about the boundary, it will be just your equation that you graphed here, but you will put an equal sign versus your inequality symbol. So the boundary line itself is going to be that y equals 2x plus 3. That's where the shading goes up to, right? It never crosses that. So that's the boundary. It's like your fence, right? If you think about the boundary of your property or something, people might put a fence along that. So that is the end of the road, so to speak. Good. Any questions with your inequalities? So really good review there, back from our algebra days, and we seem to be good to go with that. So any other questions, though, before we look at some more examples? The electric fence. Oh, good. Um, my who was it? My neighbors growing up had an electric fence, and they still do. And my kids didn't know what an electric fence was, and they were gonna go up and touch it, and I'm just like, no, don't. And they're like, why? I'm like, go ahead, touch it. You'll find out. No, I really didn't let them touch it, but yeah, funny. All right, now as we near some more of our pre-calculus concept, we're not just sticking to our straight lines anymore like we did back in our Algebra 1 days. We are going to start looking at more types of graphs. So example, we can do an inequality with the quadratic function as well. So if I have a quadratic function here, what do you think we're going to do to graph this one? So it says draw the graph of y is greater than or equal to x squared minus 3. It is going to be a graph with a solid line shading above. What is our graph going to take the shape of? So instead of a straight line, we're going to have a parabola. Yep, a quadratic equation has a parabola. So when I go to graph this, I would actually expect the shape of my parabola. And this looks like it's probably going to have a vertex of maybe 0, -3, something like that. It looks like it's probably shifted down 3 units like this. It does open up because the x squared is positive. And we can use GeoGebra for that as well. And Tommy, I think, did say that it was going to be connected with a solid line. So it is a possibility that you can have a dashed line representing that parabola. But in here, it is solid. Now, instead of shading above, because technically above, you've got pieces inside and outside of that parabola, where do you think the shading is necessarily going to be if it's greater than that? Inside the parabola? Is that what everybody else is thinking too? Yeah, it should fall inside. So greater than in this case is talking about those y-intercepts that are greater than that vertex, which is down here at 0, -3. And we are looking at filling it up inside the parabola. Good. Less than would be down here, these values, which would fall on the outside of the parabola then. So greater than, we're kind of filling up the parabola inside. Good. So no longer are we just confined to our straight linear functions or linear inequalities. We can now graph any type of function. And they all follow the same rules as well. If you're ever in doubt with where the shading should be, what's a tactic or strategy you could use to make sure you shaded correctly? So if you're ever in doubt with your shading, what's a strategy you could do? You could pick a point, and how do you check the point then? What do you mean by check it? Plug it in, right? Yeah, you're going to substitute it in for x and y in your inequality. Perfect. So substituting it into your inequality, is it a true statement? If it's a true statement after you simplify, then the shading needs to be over that point. If it's a false statement after you simplify, then the shading does not belong over that point. So very good. That is a strategy you can use to check your work to make sure that you shaded correctly. It's the area we do want. So we shade our solutions. Yep, so the shading goes over the area we do want to include. Yep. Whatever is not the solution is not shaded. We leave it blank or kind of white or whatever it may be. That may be the most powerful wizard ever, Isaias. It would probably make all the Pokemon faint instantly. My kids are still into Pokemon, obviously. All right, so now let's talk about solving a system of inequalities where we have more than one linear function, right? So at this point in the time, it might be best to open up GeoGebra and we can get a really accurate graph of what's going on here. Now, you should be able to do this by hand without GeoGebra though. So remember, the goal is still to be able to do this by hand without GeoGebra. So if I were to throw up, and I hit the wrong thing, uh-oh, where'd you guys go? Oh, I took a, hold on, now I don't know how to escape this. There we go. Uh-oh. I accidentally took a picture of the screen instead of putting the graph up. Yeah, I wanted to throw this up. And now I lost my problem here. Uh-oh. I wonder if there's a way I can take it off. I may have just cursed myself. All right, well, I do remember the first one. I think it was y is greater than an x squared, right? Yeah, so I remember that one. I can pull the PowerPoint up and see what the other one was as well. I think it was a 2x and a 3y and something. Thank you, Rebecca. Oh, you guys are awesome. See, now we don't even need the backdrop. Perfect. I'm so glad I have you guys here. All right, so y is greater than x squared. Y equals x squared. We know that's the parent function of our parabola that has a vertex at 0. So I can do like the points at 1, 1, 2, 4, and remember these would be reflected here. 3, 9, and negative 3, 9. And we can see this parabola starting to take shape. Should I connect that parabola with a solid or a dashed line? That's a dashed, yep. Okay, so, and then while I'm dashing this, should I shade inside the parabola or outside the parabola? Inside, good. All right, the next function is that, what type of function is that going to be? Like, what shape is the graph going to take on of that 2x plus 3y is less than 4? What shape or what type of line or equation or function, whatever, is that going to look like? Is it going to be parabola, cubic, straight line? What is that second one going to look like? It is going to be a straight line. How exactly can I figure out how to graph that straight line? What would you do? There's a couple different methods you can actually take here. You can isolate the y and you can put it in slope-intercept form. What's the other method that you could technically do with that equation right there? Point slope form is a thing, but we're not going to use it here. What I was thinking of was the intercept method. This is actually in the intercept form. It's in standard form, which is what they call the intercept form. You can easily cover up your variable here and then find that x-intercept. So if I want to find the x-intercept, I would divide both sides by 2 and x would equal 2. Right, so there's my first one, and then I can do the same thing with the y. I can cover up the x and solve for y, and it looks like the y would be 1 1/3, right? 4/3 when I solve there. So 1 1/3 would be like right here. All right, nice. So do I connect those 2 points with a straight line or a dashed line looking at the inequality? Definitely dashed. And then where am I going to shade for that? Below. Yep, less than is below. So now that I have 2 shadings though for this, what exactly or where exactly is my solution set? Where your shadings overlap. Good. So we don't want to lose sight of what we were actually trying to do here, and that is seeing where the two shadings overlap. So anytime we have two or more equations, we're looking for the overlapping shaded region. Good. Now this is a bounded region, right? It's kind of contained. You got boundary lines surrounding that pink shaded area where they overlap. Not every system of inequalities will be bounded like this. You can run into systems that are unbounded where it just kind of keeps going forever in a certain direction. So that's not uncommon to have either. So just giving you a forewarning with that. All right, any questions with the system of inequalities and graphing those? And remembering to look for the overlapping shaded areas. All right, and thanks to your guys' awesome memory, I didn't have to freak out about putting our grid up over our question there. Yay. All right, the last topic then we're going to kind of lead off with here, or finish with today actually, is going to be our linear programming topics. Now we do talk about linear programming a little bit in Algebra 2. Does anybody remember covering the linear programming back in Algebra 2 last year? Okay. We did a little bit. It was only one lesson long though. It wasn't anything too extensive. All right, so what the linear programming does is it's graphing a system of equations or inequalities on one coordinate plane, and you're looking for kind of the shaded region. And the shaded region will more than likely take on a bounded area of some sort. So once you find that bounded area of the overlapping shaded region, you find the corner points of that figure. And when you find the corner points, which we call the vertices, right, then we are going to test them in what we call an objective function. The objective function will then help us to identify the maximum or the minimum values of the story problem. Okay, so it's going to be your optimization problems. So a lot of companies will use these to see what's going to maximize their profit or what's going to minimize their cost savings. All right, so that's where we're going to see these kind of in the real world. All right, we do the inequalities that we can create from the story problems are what we call constraints. So if you hear that term constraints, that's the actual equations that you're going to graph, or the inequalities that you're going to graph. The feasible region is the overlapping shaded area. Okay, so these are a couple of terms that I'm just kind of refreshing you on. So if you hear me say feasible region, that's talking about the overlapping shaded area. The feasible points are those corner points or the vertex points of that feasible region. Okay, so we're going to start out with an example that is not a story problem, but they lay it all out for us. So we'll see it says find the maximum and minimum values of the objective function. So really nice of them. They actually give us the objective function. The story problems that we're looking at, we have to come up with the objective function. Usually the objective function is talking about maximizing something. So usually it's cost or profit or something along the way. So it's going to be a little bit obvious to pick out the objective function, hopefully, after reading through our story problems, because it's usually what they're trying to find a profit for. All right, the feasible constraint, or the constraints given here, they give us two, it looks like linear inequalities, well technically 4 linear equalities. It's not uncommon to have the x is greater than 0 and y is greater than or equal to 0. Most of the time we will see these as kind of boundary lines in our examples as well. So if we can't find enough feasible or constraints to make our feasible region, we should probably look at, do we need the x and the y is greater than or equal to 0? So a lot of the time that's going to be an inequality that we'll need for our constraints. All right, let's go ahead and bring up GeoGebra. We're not going to do this one by hand, only because it'll be a time-saving piece here. So in case you forget, it is geogebra.org. Oopsie, hold on. There, .org is better. And then when you click on that, use the GeoGebra Classic version. It should be the second row in the middle. Okay, once you have GeoGebra open, just enter the 4 constraints that you see on the whiteboard there. And to do the less than or equal to, remember it's just that less than on the keyboard and then the equal sign right after it. GeoGebra will change it to the inequality function for you. Okay, does everybody get the same kind of feasible region that you see on the board there that I threw up from my GeoGebra screen here? Okay, now we can see the feasible region because it's the darkest blue. The darkest blue in the middle here is that overlapping of all the shaded parts. So we need to find the feasible points or the vertices. So let's go ahead and identify the different vertices here. Let's do this first one. Using GeoGebra, where is this first point at right here? And I'll just label that point A for right now. So point A is at what value? Approximately 0. Mine's at a 4.6, I think. If I look at that, it's pretty close to a 4.6. So let's go 4.6 versus the 4.8. We have another corner point. I'll do the easiest one here to identify, B. Where is corner point B happening? 0, 0. This one's pretty easy too. We'll do C. And I'll save the kind of the best for last. Actually, I did the best first. And then there's this last one right here. Okay. And Isaias is waiting for me to go to that 1 second. I bet he had that one saved up in his chat box for a while. All right. So now that we have those corner points or those vertices of the feasible region, we test those 4 points in the objective function up here. Those 4 points are going to either maximize or minimize our functions, right? They're either going to be the highest point or it's going to represent the lowest point. Anything in the middle or in the shaded area is in between those values somewhere. Okay. Am I close with the 4.6? Because I just kind of eyeballed that instead of using my intersection tool or anything there. Good enough. Okay. We'll roll with it then. So now we are testing it back into the objective function. So we're going to plug point A in first. What do we get when we substitute the values for point A into that objective function? So 0 is in for x and 4.6 goes in for the y. About a 36.8. Let's check my notes here. All right, looks pretty good. How about 0, 0? when I substitute the point 0, 0 into that objective function, what do we get? 0. What do we get when we substitute in 5, 0? Yep. And lastly, what do we get when we substitute in the 4, 2? 36. All right, so let's talk about these values. These values are going to help us either find the maximum or the minimum of our function. So which one do you think is going to be the maximum? So looking at the values, which one's the maximum? 36.8. Yeah, this is the maximum of our function, whatever we're looking at or applying these constraints to and finding the profit or optimization from. This is the maximum. The maximum value is 36.8, and that happens at the point 0, 4.6. Okay, what's the minimum according to our values? The minimum is 0, right? That's the lowest you can go. So the minimum happens at the point 0, 0. If it asks for the actual maximum or minimum value, that's actually referring to the 36.8 and the 0. If they ask you where the maximum or minimum occur, that's asking for the point at which got you that result. All right, so this is the actual maximum and minimum values, and these are the points at which they are occurring at. Questions with how we graphed that, found the feasible region, used the vertices of the feasible region, and tested those in the objective function to find maximum or minimum values. Because this is the linear programming all kind of in a nutshell here. Now, obviously, it's not so bad when they give us the constraints and the objective function. What it gets a little bit troublesome is if they just give us a story problem and we have to come up with all of those constraints and objective functions on our own. So let's practice that in a couple examples here today. So we have a really long story problem here. It says Johnson's Produce is purchasing fertilizer with 2 nutrients, N, nitrogen, and P, phosphorus. They need at least 180 units of N and 90 units of P. Their supplier has 2 brands of fertilizer for them to buy. Brand A costs $10 a bag and has 4 units of N and 1 unit of P. And brand B costs $5 a bag and has 1 unit of each nutrient. Johnson's Produce can pay at most $800 for the fertilizer. How many bags of each brand should be purchased to minimize cost? All right, so this last sentence, how many bags of each brand should be purchased to minimize cost? Anytime it's trying to ask you to minimize or maximize something, that is your objective function. So we generally want to start by finding the objective function. All right, so to find the objective function, it says to minimize cost. So we're looking at the cost of each brand. What is the cost of each brand? $10 and $5 respectively. Okay, so let's call brand A our X variable. So is that okay? Is everybody good with that? So objective function equals cost. We'll have $10 times brand A plus $5 times brand B, which we'll call our Y. So there's the objective function that we're going to plug our vertices into to try and find the minimal cost, right? So which one's going to be the lowest? All right, now we need constraints to graph because we need to find this feasible region. And this story problem is set up really confusing. Does anybody have any suggestions for constraints that we can use for this story problem? So in other words, can anybody think of any inequalities that we can come up with for this? Yeah, so obviously we've got to do greater than or equal to 0 for both brands, right? Because you can't make a negative amount. So at least we got that out of the way. Now there's just a few other things that we need to take into consideration. How about the brands themselves? Let's talk about the 180 units needed for the nitrogen. And let me take a look. If the nitrogen here, how many units do we need of nitrogen in brand A? So brand A has how many units of nitrogen in it? 4 units. Okay, so we're going to do 4 units from brand A plus how many units from brand B? So how many units of nitrogen are there in brand B? There's only 1. So 1 unit of nitrogen from brand B, and it says they need at least 180 units of nitrogen. So at least is what inequality? Greater than or equal to. All right, so there's one constraint we can have. The other constraint, let's talk about the phosphorus then. So now we need an inequality for our phosphorus. How many units of phosphorus are in brand A? There's 1 unit of phosphorus from brand A, and then 1 unit of phosphorus from brand B, and they need at least, so greater than or equal to again, the 90 units of phosphorus total. So we're taking a look at the nitrogen from each brand and creating an inequality, and we're taking a look at the phosphorus from each brand and creating an inequality. I think we can also create an inequality for the cost as well. So we have the 10x plus 5y, and yes, that's going to help us with the objective function, but they also give us another constraint here that Johnson's Produce can pay at most $800. So if I take the cost, what inequality symbol should I use for at most? Less than or equal to 800. All right, I think we got all the constraints that we need here for this problem. And there's 5 of them total. So we do not graph the objective function, by the way. So that does not get graphed. Only the constraints do. So these 5 inequalities right here. So let's go ahead and go to our GeoGebra. And see what our feasible region is going to look like here. Massive. We obviously got to zoom out a lot, right? Because you're talking about 800. Luckily for us, though, I think it looks like it's taking on the shape of a triangle almost. Let me throw up what I see when I graph those. Sorry, got to cover the inequalities a bit. Is that what everybody else is seeing there? Something similar to that? So the feasible region is the darkest blue, right? So the darkest blue is happening in this triangular shape right in here. So there are 3 vertices that we need to find. And we're probably going to have to use GeoGebra to the best of our ability here to try to get as accurate as possible with these corner points. Let's start with point A at the top there. So point A is happening at what value? $10,140. Yep, that's what I see as well. Let's check out B next, if anybody can find where B is occurring. Oh no. 3060, okay. I was just trying to move this over. Isaiah is going to confirm that, and then we just need C. $70.20, thanks. All right, so those actually turned out pretty nice for those vertices there of the feasible region. Now to find optimization, we are going to substitute these 3 points into the objective function that we created. Remember, the objective function was looking at our cost, so that's where we got the 10 and the 5 from. So let's start with point A. What do we get for the cost if we buy 10 bags of brand A and 140 bags of brand B? What is that going to cost us? $800. All right, what about option B? So buying 30 bags of brand A and 60 bags of brand B. What is that going to cost us? $600. Okay, and then lastly, if we buy 70 bags of brand A and 20 bags of brand B, another $800. Ugh. All right, what were we trying to find with this story problem? Were we trying to find maximum or minimum? We were trying to find minimum cost. So what's going to be our minimum cost? $600. All right, the question asks, how many bags of each brand should be purchased to minimize cost? So to answer that question fully, what should our answer be? 30 bags of brand A and 60 bags of brand B. Perfect. So 30 bags brand A and 60 bags of brand B. Good. And then the minimum cost, it doesn't ask us this, but the minimum cost would be our 600. Okay. Any questions with that story problem there? Okay, one last story problem for us today, and I think if we just set up the constraints and the objective function, that'll be good enough. We don't have to fully go through it all, because I think the hardest part with these story problems is just getting the constraints and the objective function set up properly so that you can use GeoGebra to graph, find the vertices of the feasible region, and then use substitution. So let's take a look at this one. It takes 13 units of carbohydrates and 7 units of protein to satisfy Ralph's minimum weekly requirements. The meat contains 2 units of carbohydrates and 2 units of protein per pound. Cheese contains 3 units of carbos and 1 unit of protein per pound. Meat costs $3.60 per pound and cheese costs $4.50 per pound. Find how many pounds of each are needed to fulfill the minimum requirements at minimum cost. All right, so if we can start with the objective function, that's the best place to begin. So we're trying to optimize, let's see, How many pounds of each are needed to fulfill the minimum requirements at minimum cost? So minimum cost is what we're essentially looking for there, right? So we're going to set up an objective function for the cost of each item. So let's start with, I guess meat was the first thing that was introduced. So let's let that be our x variable. How much is the meat? $3.6. And then cheese was the second thing introduced. So we'll let that be our y. Yeah. All right, is everybody good with just setting up the objective function? So again, usually the objective function is talking about profit or price of some sort. Generally, not all the time, but most of the time is what you're trying to find the maximum or minimum of. So what are you trying to find the maximum or minimum of? The cost in this example. So that's where your objective function comes into play. All right, let's talk about the constraints. So the inequalities we can create now for the story problem. What do you guys got for me? Can you think of any inequalities we can use for the constraints here? Yeah, so x is going to be greater than or equal to 0, and so is y, because you can't have a negative amount of meat and cheese. Where is a 13? Ooh, so 13 units of carbohydrates. Maybe we should talk about carbohydrates first. So if we're talking about carbohydrates in general, you have to look at each product individually. So let's start with the meat. How many carbohydrates are in meat? 2 units of carbohydrates. So we'll let that be a 2x. Now you have to take into consideration their carbohydrates in the cheese. How many carbohydrates are in cheese? 3 units of three units of carbohydrates in the cheese, and it takes 13 units. So what do we do? What inequality symbol should we use there if it takes 13 units? Greater than or equal to. Yep. All right, what's another inequality you're thinking of? So you got carbohydrates out of the way. Yeah, you're going to need one for protein. All right, so you look at protein now, 2 units of protein from the meat, 1 unit of protein from the cheese, and it takes 7 units there altogether. Good. All right, so those are your constraints. Because it doesn't give us a maximum amount we can spend, right, or a minimum amount we can spend, there's no constraint that we can create for the price. So the price is strictly just going to be kept for our objective function this time because they don't give us an actual minimum or maximum value that we can spend there. So we cannot create a constraint for the price here. All right, that would be what you would go and plug into GeoGebra to find your feasible region of. And then you would test those corner points and look for the lowest value, right? Because you want the minimum requirements. All right, questions with how we created the constraints or the objective function? Because like I said, I think that's going to be the trickiest part of the linear programming stuff. Okay, it takes a while to catch on with setting up those constraints, but the more practice you get, the better you'll become. All right, that's all I have for you today on the 7.04. Woohoo! If you do have any questions, I do have office hours available tomorrow. I'm booked for today, but there are still some spots open for tomorrow. Or send me an email if you need me before class next week. All right, so I will plan on seeing you guys again next week, Tuesday. Bye, everyone. Have a great weekend.